All right, thank you, Diana. All right, so we're gonna get started with our 6.2 where we left off last week. And we're actually gonna go over that exit ticket that we had at the end of class, okay? So I'm gonna go ahead and share my screen. We'll go ahead and do that question because all I asked you to do is set it up. So I wanna make sure we're really clear on how to set up the different parts of it. And then it feels like, and it sounds like you guys are doing really well with the evaluating part, but again, we really wanna focus on the setup and make sure that that's where we feel really confident because I'm so glad that you can integrate. And that is definitely an important skill, but I also want us to make sure that we know how to set things up accurately so that whatever we start to do for the problem will actually give us the correct answer at the end, okay? So let's get started. All right, can you guys see the screen?
Yes.
Cool. All right, so at the end of class on Thursday, we had, let's just kind of go back in our notes a little bit. We had started to take a look at a situation where, wow, my diagrams were really bad last time. We were looking at situations where we had a hole inside of the solid. So it wasn't a solid shape, but there was like a piece carved out of it. And so what we needed to do to take into account that hole or the missing part is that we needed to have an outer radius and we needed to have an inner radius and we needed to subtract the two, okay? And so we were able to do one problem together towards the end of class. We took a look at example number 10. We spent some time looking at that I have to say you guys are doing really well so far is in all the work I've seen, I haven't seen anyone mix up X's and Y's together in the same equation. So that's something that you should be super proud of because I think that's a hard thing for folks to understand. So we were able to find our big radius and our little radius based off of our diagram. And I just want to review real quick how we tell which one is your big radius and how we tell which one is your small radius. So I'm going to go back to this middle diagram for a moment. Okay, so this middle diagram, the axis of revolution is right here. It's right at the y-axis. And if I kind of erase that and that and that for a moment, the curve that has a greater distance from this axis of revolution is this blue one right here. Okay. So because the blue curve is further from the axis of revolution, that is your big radius because it's a greater distance, okay, from this yellow line. To find your small radius, you have to find the curve that is closer to your axis of revolution, which in this case was our red one, okay? And so that's why when we did pi big R squared minus little r squared, we had the big R as this 4y, and we had the little r as the y cubed, all right? So a lot of it comes from your diagram, which is why I'm having us spend some time looking at these pictures, drawing our pictures, and really trying to understand how, like, which one is further away, okay? So then at the very end of class, I said, hey, I want you guys to take a look at this problem and set it up. And so let's go through that setup together right now, okay? So we have determined the volume of the solid obtained by rotating the region bounded by these two curves about the x-axis. So I know that my axis of revolution is this line right here,
okay? Now, even before I really look at the pictures below, which curve is going to be my big R and which curve is going to be my little r?
Y equals 2x squared is the bigger r
Yeah, what's your reasoning there?
because it's further away from the axis of revolution.
Yeah, so if I draw a line from the blue curve straight down to the axis of revolution, I have to go past the red curve to get there. And so that means that that one is further away, and therefore it's going to be our big radius. Good. Okay, well, since we only have two curves, that means the other one must be our small radius. But we can also see that when we draw that vertical line, that the distance from the red curve to the yellow line is shorter than the distance from the blue curve to the yellow line, okay? So this y equals x cubed is my little r. Now, when we think about this small slice and we're revolving this, okay, what we end up with is a case like this, where basically we have a funnel and the inside has been scooped out. Okay, we have sort of like a very thin piece of the solid, so like between this part and like this part, okay, but most of this part, like this light pink part, that is not there. That's like empty space. Okay, and so maybe the best diagram for us in this case is this last one, where we can see that the curves, and I think they changed the colors on us. The curves here, we have our outer radius and we have our inner radius. Okay, and together that will give us the washer that we need to set up. Now, since we are doing our volume, we're going to set that up as volume equals pi, the integral from a to b of big R squared minus little r squared dx, okay? Now, I saw a few of you maybe in like panic mode, or like I didn't really want to think about it too hard on a Thursday mode, but some of us put in the curves correctly. So we had pi, and then we had 2x squared squared minus x cubed squared dx. But then when we were putting in our bounds, and I saw this for a few folks, they were like, oh, 2,8, I should use both of those numbers. And then they put a 2 down here and they put an 8 down here, up here. Okay. But keep in mind that the bounds should not come from the same point, because what you have right here, the bottom number is an x value and the top number is a y value. And that's the one no about our setups, right? We have to have all x's and dx's or all y's and dy's, right? So that's one reason why this 2 to 8 is wrong. But the other reason why it's wrong is because it doesn't give us a starting point and a stopping point, all right? So if we get rid of that and that and that, all right, I think we were using purple last time. I'm looking for these slices. Where do I start counting those purple slices? Like what x value?
Zero.
Yeah, I'm starting here at x equals 0. So that means my bottom bound has to be 0. And then I know I end when I get to this point, but I better not pick 8, because that tells me that you're not sure what's an x value and what's a y value, okay? So I really want to make sure that we know we have to pick the x value here. So we're going to stop at 2. All right. Does that clarify the setup for folks, or does anyone have any questions about why you can't do it another way, or okay. So let's take a moment then and go ahead and solve this, all right? So at the end of last class, I said I just want the setup. And so now let's go ahead and solve this, okay? So I'll give you a couple minutes to start working on solving this integral, and then I'll start to put my work up on here as well. All right. So just a couple of things I want to highlight here. When we square our terms, we need to make sure we square everything inside the terms, right? So like we have to square the 2 and we have to multiply that power by 2. That's how we get 4x to the 4th. Similarly, this 3x to the 3rd squared will give us x to the 6th power, not x to the 5th power. Okay. Now from there, we can go ahead and integrate. So we get 4x to the 5th over 5 minus 1/7 x to the 7th. And then we plug in our bounds, 2 and 0. And a lot of times I do sort of more of a visual check, and I see like if I plug in 0, is it going to give me 0? And then if it does, I don't necessarily write it out. Okay, but it is an intentional thing that I check. I don't want to get into the habit of just always making that last term 0. Okay, so from here we can go ahead and plug in our 2, and so we get 4/5 2 to the 5th minus 1/7 2 to the 7th, and then when I plug in 0, it's going to go to 0. Okay. That gives me 1/28 over 5 minus 1/28 over 7, and that has a common denominator of 35, and then when I subtract my numerators, I'll end up with 256 pi over 35. All right, are there any questions about the setup or the solution for question number 11? All right. Well, then let's jump into another example and let's practice more of these, because I think the more we do, the easier it gets. All right, so let's take a look at this example. All right, so this example, those training wheels are coming off. We don't have a diagram anymore to rely on. We need to think about how we draw these diagrams on our own. So it says determine the volume of the solid obtained by rotating the portion of the region bounded by x squared minus 4x and x equals 0 about the x-axis. All right. So if we're going to set up our diagram, then we need to know what the curves look like. All right. So if I take a look at the y equals x squared minus 4x, and let's go ahead and do that one in orange. Okay. It might be helpful. Like, I know it's a parabola, I know it faces up, but sometimes being able to find the x-intercepts helps me draw a better, more accurate picture. So let's see, if I go ahead and find a greatest common factor for this, I can take out an x, and then I'm left with x minus 4, which means that this parabola crosses the x-axis, so it has x-intercepts at 0, 0, and 4, 0, because 0 and 4 are the two values that make this equation equal to 0. Okay, so let's see what that looks like on a diagram. All right, so I know my parabola is facing up. I know it goes through the x-axis at 0 and at 4. So really I have like this kind of shape down here. And this coordinate is 0, 0, and this coordinate is 4, 0. Now the other bound for this shape, because we need to sort of seal the shape off, is this x equals 0. And x equals 0 is, I think I meant to say y equals 0, sorry. Y equals 0 is going to be the x-axis, and that will give you that right there. Okay. So now I'm going to go ahead and draw in my axis of revolution, which happens to be the same as one of the boundaries. And so when I think about what my reflection looks like, I'm going to end up with something kind of like this at the top. Okay. So in this case, am I going to use a formula that looks like pi r squared, or am I going to use one that looks like pi big R squared minus little r squared? So let's make that decision first. Do we use the one with just the little r, or we use the one with the big R and the little r?
Just the little r.
Just the little r, yeah. What's your reasoning for that?
Because there's no hole in this one.
Yeah, there's no hole, exactly. Okay, so because there's no hole, we want to use this one. All right. Now, one more question for you. Should we use dx or should we use dy?
Dx.
All right, so folks out there, if you're thinking, well, how do you know that? You could draw some vertical lines and you can draw some horizontal lines just to kind of check, okay? So let's say I thought maybe I should use dy. I would draw lines that would go this way. But those lines go from orange to orange, and that for us right now is problematic. okay? So I'm going to undo those two, and I'm going to try drawing them vertically. So if I try drawing them vertically, is there a clear top curve and bottom curve for every single purple line? And the answer is yes. We have the pink curve on top and we have the orange curve on the bottom, all right? So because all these lines are stacking along the x-axis, we can say not only are we using pi little r squared because there's no hole, but more specifically, we're using pi, the integral from a to b of little r squared dx, okay? Now, I only want to do one last step here, which is what is our equation that we use for our radius? Okay, so what do we use for our little r? And what do we use for our a and b? So any ideas on what we use for a and b?
A and
Zero
B.
to-
Oh, you can go.
Thanks, man. 0 to 4.
Yeah, we're going to choose our x values. So we're going to go from 0 to 4. All right. And then how do we define our little r or our radius?
Would it be x squared minus 4x?
Okay, so if we had x squared minus 4x as our radius, all right, then what is that going to do for us? That is going to give us, yeah, that's going to give us our distance for each one of these lines right here, and then we square that, and that will give us our r squared, okay? Now this problem should look familiar because we did this one in example number 9, okay? But I feel like sometimes when we're working through problems, we sort of get so focused on each problem as we're doing them that sometimes we lose sight of the bigger patterns here, okay? So as you're studying, this might actually be a good thing to do, like if you have a study group, to be like, hey, let's just take a moment and set up a bunch of these, talk through the setup. How did you know this was dx? How did you know that was dy? How did you know that we needed little r squared only and we didn't need big R squared minus little r squared? Okay, those are all really great conversations that you can have with each other to help you maybe build that understanding a little bit more for yourself, okay? Now, one last thing for this one. No last things for this one. Sorry, that's it. All right. Let's go ahead and take a look at one last example here, okay? So let's take a look at example 13, all right? And I'll give you folks a moment to start to sketch the graph for this, all right? Along with where's the axis of revolution. I don't see any bounds here, so it might be really useful to find some of those intersection points either algebraically or on your graph, okay? All right. What are folks getting for the one in the orange, the x equals y squared? What shape is that? What direction is it facing?
It faces towards the right.
Mm-hmm. Yeah, so you've got a parabola, but it's opening, goodness, but it's opening towards the right. Yeah, so you've got something kind of like this. Okay. And then what about this one in the pink? What does that curve look like?
It's a line.
It's a line, yeah. Tell me a little bit more about that line. Positive slope, negative slope, y-intercept.
Positive slope.
The positive slope, yeah. What's the y-intercept?
Y-intercept at 2.
Yeah, -2. So we've got a line that looks something kind of like this, okay? And this point right here is 0, -2. And so once I've drawn my shape, I realize they didn't give me bounds because this is a fully enclosed shape. And so it's up to us to find the coordinates of this point down here and this point up here, okay? So a lot of times I've said, all right, well, if you need to find the intersection points, that you set them equal to each other, all right? In this case, can I set them equal to each other? Like, how do I go about finding these intersection points?
You can solve for x in the pink equation and then set them equal.
Perfect, I love it. So let's get this x all by itself, right? So then I'll get x equals y plus 2. And now I can take y squared and set that equal to y plus 2, all right? So let's see what that gets us. Y squared equals y plus 2. General approach here. How do I start to solve this kind of question?
Set equal to 0.
Set it equal to 0. Good. I see that quadratic and I'm already thinking move everything to one side, set it equal to 0. All right. And luckily this is factorable. So I can factor this into y minus 2 times y plus 1. And that means that y equals 2 is one of the intersection points and y equals -1 is the other intersection point. So this point down here has a y value of -1, and this point up here has a y value of 2. Okay. Now, if you come into this orange equation, you can find the value that goes with it. So for example, for the top point, y is 2, that means x is 2 squared, or 4. And for the bottom point, y is -1, so -1 squared is 1, and that gives you the x value for the bottom point, okay? Now you might not need those, but I think sometimes I like to, when I'm in the zone, I like to just find all the values in case I need them later, okay? But you don't have to, you can sort of wait and see if you need them. That's absolutely fine as well. So based off of what we have here, all right, let's go ahead and draw the reflection around our axis of revolution. So my axis of revolution this time is the y-axis, which means that it's right here, okay? And I'm only going to reflect the part that I need, which is this point to this point, and I kind of have something like this. Okay. Looks like a butterfly. So pretty for a Tuesday morning. All right, so we have this is revolved around the y-axis. Now, if I think about which direction I should draw my rectangles, what are folks' thoughts? Do we think we should draw lines that are parallel or perpendicular to the y-axis?
Perpendicular.
Perpendicular, all right. So if I drew ones that were perpendicular, they would look something like this. And like this, okay? And no matter where I draw those purple lines, every single purple line has a right curve of the pink line and a left curve of the orange line, okay? So that is a really good way to set things up. It also means that if I'm going to be stacking these up the y-axis, I'm going to need these y values for my bounds, and that means I'm going to need to use dy, not dx, okay? So last thing we need to decide, do I need pi little r squared or pi big R squared minus little r squared?
Pi r squared.
Why do we think pi r squared?
Because it doesn't have like kind of like a circle in the middle or an opening.
It actually does. It has a, so one way that you can tell is if you're drawing your purple line, like if I draw the purple line here, that touches the axis of revolution, right? So at that point, there's no hole. But what about this line? Does this purple line ever touch the yellow axis?
No.
No, it doesn't.
It doesn't. So the moment you see that one of your slices is not going to touch the x or the axis of revolution, that means that you have a hole, okay? So like maybe this one is a little bit more drastic. That purple line is so far away from the axis of revolution, there's definitely going to be a hole up there, okay? So if I took like this slice up here, that would look like the pink curve would make a circle around the outside, and then the orange curve would make a circle on the inside. Okay, so this is a case for washer where we're going to have big R squared minus little r squared. So we have pi, the integral from c to d, of big R squared minus little r squared dy. Now we've said that we're going to set up our y bounds. So we already circled them earlier. Our c is going to be -1 and our d is going to be 2. Which one of these curves is the big R? Is it the linear one or the quadratic one?
The linear.
It's the linear one, right? Because the pink curve is further away from that axis of revolution. It is the right curve on every single one of those purple lines. So we're going to take the equation, and we're going to, instead of putting y minus x plus 2, we're going to put y plus 2 squared. Okay, because we need our equation to be in terms of y. So minus, that means that the orange curve is our little r. That one's already solved for x, so we can write that as y squared And that's my little r, so I have to square it because it's little r squared. Okay. Are there any questions about this setup so far? Okay. So I'll give you a few moments to start solving this, then start evaluating it. So whatever you need to do to algebraically simplify this, and then you're going to plug in your bounds, and let's see what we get. All right. So definitely some places here for some sign mistakes, right? So we want to be really, really careful because our bottom number is not 0. In fact, it's a negative number. And so we're going to need to make sure we double check all of our signs, okay? But hopefully when you were simplifying your initial expression, you FOILed out that y plus 2 squared, okay? And you should get y squared plus 4y plus 4, and then minus your y squared squared, which gives you y to the 4. And so each one of these terms, we can just use the power rule. We get pi times y to the third over 3 plus 2y squared plus 4y minus y to the fifth over 5. Now, again, don't get in the habit of saying, oh, that second term's always going to go to 0. Make sure you try plugging it in your head and that you actively make the choice. All right, this one is 0 versus this one's not, okay? I didn't show all of the steps here. So if there are any questions about how I got from one step to another, please let me know. Anybody else getting this answer of 72 pi over 5? I believe that's the right answer.
I forgot to factor or did a y plus 2 thing, so I did the whole problem without.
Oh, okay.
So I'm just gonna redo it.
Okay, no problem, no problem. All right. So as folks are finishing up, I just want to give you that on the whole screen so you can take a look at that. All right, but that's actually going to end our lesson for 6.2. All right, the rest of this practice packet or lesson, there's 4 more questions. All right, so I just want to talk very briefly about them, but it's not going to be something that we cover in this class. Okay. So just so you're aware, everything that we've done so far has had an axis of revolution that was either the x-axis or the y-axis. It is entirely possible and actually quite common for you to encounter situations like this where the axis of revolution is not the x-axis or the y-axis. If you feel really confident with the stuff that we've done already, then this could be a good sort of challenge place to think. But if you're like, I'm really just struggling to make sure I set up my, regular situations where I have an axis of revolution of the x-axis or the y-axis, then that is a place where you should definitely spend the time, okay? So there are some extra practice here if you'd like to take a look at those, but you don't need to. These will not be on the final exam, okay? I think if anything, they may come up a little bit in Calc 2, more in Calc 3, but again, I think we're all on different trajectories, so so it's not the end of the world if we don't get to this particular topic, all right? Are there any questions about 6.2 before we take a break?
I have a question on the problem that we just did.
For sure.
In one of the steps, where did the 9/3 and then the +2 come from?
Okay. So the 9/3 I got with the 8/3 plus 1/3. Gave me the 9/3.
Okay, got it. Thank you.
Okay. And then the 2 came from 2 minus 4, which is -2, but then a -2 gave me a +2.
Okay, so you just like combined both of those parentheses.
Yeah.
Okay, thank you.
Mm-hmm. All right. Well, if there are no other questions right now, then let's go ahead and take a break right now. So it's 10:28, 10:29. Let's be back at 10:40.